Thank you all for being here. My name is Tamir from Succinct, and I'm going to talk about the continuation argument we use in SP1. So the short outline of the talk is we're going to start with like an overview of the basic architecture of SP1. Then we're going to mention the problem of splitting like large proofs. Then talk about the succinct solution, or just the succinct solution. And then we'll see the trade-offs with this solution, the implications, and then hopefully have time for questions. So SP1 is a new general purpose ZK that we released last month or so. And just a few details about it. It's verifying RISC-V instructions, and we use fry over the baby bear field. This might change soon with circle SNARK, but so far we're using baby bear. The arithmetization is based on an air, or as you would know it as a STARK, with lookups, so a STARK air with randomness. And one of the key principles is to have a modular design so that it's really easy to add other tables, or as we call them, precompiles. So how does it work? What's the basic architecture? So in the most basic building blocks are the air tables. So for every simple unit of logic, we have its own air table. So we have a table for a CPU, we have a table for Ketchak, we have a table for elliptic curve operations, and some people that in the community added their own tables, and they can easily integrate it into SP1. And it doesn't matter how many tables there is, you only pay for the tables you use in our prover. And the missing link for them is that they communicate through a bus that is based on some, I'll later explain how it's implemented, but basically like what the bus is you can send, every table can send arbitrary tuples of information into the bus with a certain multiplicity. And the bus argument is that all the multiplicities add to 0. Another nice thing about this bus argument is that the memory check that we have is also implemented entirely in the bus. So there's no memory table. It's just sort of a virtual table. And it's all through the lookups. It's this memory argument by Bloom et al., offline checking of memory. Now, let's see how this works, really. So let's say I want to execute the instruction add. So I'm going to use the same symbol for the registers and the values, just the same notation. So I want to fetch the values in B and C, and put in A the sum B plus C. So these are U32, or I32, whatever you want. Then the CPU will the CPU table will have a row that says the instruction is now add on A, B, and C, and these are the values. And it won't prove that A is B plus C. It will just put this tuple, the clock cycle add A, B, C, into the bus with multiplicity 1. So now the bus is loaded with this thing, and someone has to take it in order for the argument to work. And the ALU table, which is responsible for all the U32 operations. Actually, the ALU is several tables in our implementation. Will contain a proof that A is equal to B plus C, and will send this tuple into the bus with multiplicity -1. -1 is really just P minus 1. And this is using lookup, but again, it can be, any permutation argument works for this. I'm just using our own convention. So this is nice, I can just do this. Let's see what happens with the precompile. So the same principle, let's say I want to make a Ketchak permutation, and I have the pointer to the sponge state. Then the CPU will just say, oh, Ketchak permute this sponge slice, and put the pointer into the bus. And the bus will then have to satisfy it. So the Ketchak table will actually interact with memory on its own, because everything is done through the lookup. We'll make the proof that it's valid, and we'll put the same tuple back into the bus with multiplicity -1. So that's basically how everything is glued together. Great. But now, what is the challenge? So as any ZK VM general purpose has to do, if we have a large execution trace, we have to split it into several proofs. Well, first, it's necessary because the size of the trace is limited, especially in Baby Bear, where it's really like just 2 to the 26 or something. So we really hit that limit. Also, proving large traces takes a long time. There is asymptotics that are unfavorable for large traces. And most importantly, actually in practice, more parallelism is enabled with smaller shard sizes. So if my shard, for example, we use like 2 to the 19 right now as default. You can change it as it's just a variable you can change. So really, like, then you can just prove stuff in parallel, and it's completely parallel, almost, we'll see. But basically, you can enable more parallelism, control latency, and lower your costs. Now, how do we split the claim? Really, there's two stuff you have to do. So SP1, so the boxes that I showed earlier, has two things. There's the boxes themselves, the traces. Each trace is just an error table. So you have to verify the table constraints. So there is initial constraints, final constraints, and transition constraints. Then you have to verify the bus argument, that each multiplicity sums to 0. Now the first part is actually not a problem, because the error is already kind of like local, you can just cut the table at any moment, and you can split your table, that's fine. The problem is really the bus argument. How do you, like, now that you split the table, the sum is no longer 0. So how would you even verify that? Or how would you even do a bus argument with independent proofs, if you guys know how permutation arguments are actually implemented? So this is really the big problem. So really the problem is how to split the bus argument. And how would you do it? So the common solutions are usually make your transaction, or like your atomic unit of execution, small enough that you can just stop the program, start a new program. You don't have to save any state. Another thing, which is, for example, what RISC-0 does, is modify your claim so that there's really no interaction in lookups between the different shards. So in RISC-0's thing, they will Merkleize some of the memory, so they commit to the memory state between continuations. And we kind of like, when we were going to implement our continuation argument, I was really kind of lazy to do that. I just didn't want to do it. So I was trying to think, like, what if we try to pretend that it's really just one proof? And maybe not split exactly in the beginning of the proof, but split in some other way. So you can pretend, but this pretense has a cost, like any pretense. So in order to understand this cost, we have to kind of know how the bus works. So this is the most equation-heavy slide. Bear with me. So how does the bus work? As I said, you can send arbitrary tuples into the bus, but with some multiplicity, and then someone else has to pick it up in order for the argument to be valid. So what do? Let's say you have a tuple, T0, T1, T2, like our add ABC clock tuple that we had before. First, I'm doing that by using verifier challenges. So I'm getting 2 challenges from the verifier. The first challenge, alpha, I will use to fold the tuples into one value. So these challenges are in an extension. For Baby Bear, they're in a big field. They're in an extension field. So first, I will fold these tuples into one extension element using this first challenge, alpha. Now that I have a folded thing, I can add it to our bus. So our bus is represented by one value, really, in the extension field, initialized to 0. Every time I want to input something into the bus, I add, with some multiplicity m, I add m over beta minus this Reed-Solomon fingerprint of it. That's just the name of it. But it's really just folding it as a random linear combination with powers of the challenge. And because all these denominators are unique, so this is basically the idea of lookup. I can do any multiplicity here, and it's really cheap to change the multiplicity. And each value here is unique, so it will only be valid in overwhelming probability if all the multiplicities match up to 0. Or if and only if this sigma bus is 0. So this is what we want to split. So if we want to split this between shards, what do we need? First, the basic thing, the basic issue, is we need them to share alpha and beta. But alpha and beta are derived from fiat Tamir. So we can't just like take values derived in one shard and use them in another. We have to have everything inside the fiat Tamir. Of course, there was a talk about this earlier today. Everything must go into the fiat Tamir. So how do we do this? Well, we can still do this by paying some cost in complexity of execution. So I kind of made my work easier, but the work of all the people doing the cluster stuff is harder. But I assured them that it would pay off, and so far it seems to pay off. So what do? We basically commit to all the execution traces of these tables without doing any permutation stuff. And that is part of the computation that is usually, for us, not the bottleneck. So we do this computation, and then we can load the challenger from this. This is how if you had one proof, this is what you would do. So this is the pretend part. You get those random challenges, and now you can do Frey proofs separately. So after the challenges, you have constraints and proofs. And the important thing, though, is all those shards have to start from the same challenger that has the entropy from all of them. So there is a two-phase process. Instead of continuation being a one-phase process, it's a two-phase process. But it saves a lot of overhead. It's basically zero overhead on the continuation. So that's basically was our reason for it. And we kind of we started from the fact that this is easy, and if we want to change it, we can change it, and we still might. We'll see in the end if this is only the version 1. Maybe it's in the end will be more efficient to do other things. So what are the advantages of disadvantages? So for us, the advantages, first it started with just continuations, but actually then we found more advantages. So zero overhead for the memory, but then we can also realize it made it easier for us. We had another problem. What about precompiles? So if I have a long program, if I have a few billion cycles of a program, but only a few hundred catch-acks, I don't want to have a catch-ack at every shard. I want to have catch-ack in one shard. So obviously we could do that without this scheme, but this scheme actually gets zero overhead on that too. So one shard can have only catch-ack and just put all the catch-ack stuff in the bus and not know about the CPU. So we can prove the catch-ack separately and prove even the add instruction separately, and we can divide the shards however we want. So that's a really nice solution we got from that. Our shards don't have to be causally related to each other. They can do whatever they want, as long as each table is correct and as long as the CPU is correct. So the CPU is kind of like the king of this proof. So that was really nice. So yeah, so the last point is this aggregation of different operation across shards, right? So I can use only one shard for a precompile. Of course, the disadvantage is I have to wait for all the commitments to be computed before I start proving. So it's a two-stage process instead of a one-stage process. But we actually found that there's not much overhead. Naively, you maybe have some communication overhead, but we kind of eliminated that. But just when we continue proving, every shard will just recompute the commitment of the main trace, which is really, again, not the bottleneck and really fast. So we found that this was very minimal communication overhead. The only overhead is, of course, a two-stage process. Another issue, though, is, of course, you cannot execute arbitrary programs like this. If you have a single proof, the security of your proof is limited to the length of the entire trace along all shards together, because that's what the challenge is canceling out. That's what if you know the Schwarz-Dissipel lemma, this is what appears in the denominator. So of course, this is a limitation, but for us, it's actually not a problem because the only programs you will prove in ZK are small enough that it's fine. Or if they are so long, it means we need more precompiles maybe. So in practice, we didn't really have an issue with that. The number of shards is usually controlled. And again, we'll have soon we'll have also like a little assert that will tell you your program is not kosher. But again, this is not happening. So to conclude, we went through the basic architecture of SP1, and actually any like lookup-oriented VM also is basically looks like that, or most VMs. Like RISC-0 is a little different, but a lot of lookup-based VM kind of look like that. Then we talked a little bit about continuations, and really it's just about the bus. Our solution was to share challenges via a two-stage process. And for us, there's a lot of advantages, which is like zero overhead, very simple in the code. The code is very simple because the arithmetization doesn't have to account. We don't have to augment your Rust code with like hashing memory tables and do more syscalls of memory management. And so it's faster, cheaper proofs. And we also have flexibility in organizing the workload, which we experimented with a little bit, and it could be beneficial. So like, for example, some machines can be heavy and do the big tables, and some machines can also do the small tables. So it's kind of nice to have that. And that's basically all. Questions?
Thank you very much. It was a great talk. We are officially on break, but if there's like one question, a quick question here, can we get the mic? That would be, can you come to the front?
Hello, thanks for the talk, very cool. I was wondering, for security, do you need multiple challenge because you're working on a small field?
No, so it's actually the challenges are already in a big field. We take challenges that are in an extension field of degree 4.
Right.
But you need two challenges because you're doing two different things.
Yeah,
because you're also folding. So they have to be orthogonal to each other. So you're first folding, and once you folded, you do this. Also, like if you notice, another fun thing for that is here we need to have the clock here to make the message unique. So there's a lot of we have to make sure the messages are unique and the multiplicities are really representing what they are.